we were discussing about anisotropic etching, and in the last class we have discussed like how KOH can anisotropically etch silicon. Now today we will talk about one new chemical, that is tetramethyl ammonium hydroxide or TMAH, and TMAH also etches silicon anisotropically, means in all the direction the etching rate is not same. Now as you understand by now that the etching rate is depends on the silicon crystallinity or which direction we are etching. So changing the chemical, that property does not change. That means that the 100 will have like the medium kind of etching rate, 110 will have the highest etching rate, and 111 will have the lowest etching rate. But in those directions etching, like the magnitude of etching rate will change definitely with different kind of chemicals. So first of all, what are the advantages of using TMAH? The first point is that this is very much less toxic, like KOH is more toxic than TMAH. Then this is highly selective to oxide and nitride compared to KOH. That means like if we compare that how much of oxide is etched in 1 minute in terms of KOH and TMAH, then in TMAH the etching rate like the oxide etching will be lesser. So this gives us high selectivity. That means that as we know that these oxides are actually used as masking layer, right. So as we discussed earlier that if we have to etch 10 micron of silicon, and in that time if we need to etch, let us say for 30 minutes for that, and by that time if the SiO2 is etched by let us say 100 nanometer, then we need at least 100 nanometer of SiO2, otherwise the masking layer will get etched off. Whereas for TMAH this etching rate is even smaller, so we can use even lesser thickness of masking layer if we use TMAH etching. In the silicon, for the silicon the etching rate is pretty high, like comparable to KOH or even higher. And then the fourth point is the most important, that is the compatible with CMOS processing. That means like whatever microelectronics or sensors we use today, all are based on CMOS circuitry, and for that all the processes are not actually compatible of CMOS process with the CMOS devices, but TMAH does not do any kind of harm to the CMOS device, or it does not change the mobility of the semiconductor. So it is compatible with CMOS processing. Now here we are comparing silicon etch rate with TMAH concentration, right. So as you are saying that as we increase the TMAH concentration, then the silicon etch rate decreases, and it goes from like these graphs are drawn at different temperatures. So at 70 degree centigrade the etch rate is the lowest compared to the other two temperatures. So another point what you can note from this graph, that as we are increasing the temperature the etch rate is getting higher and higher, whereas as we are increasing the concentration etch rate is getting smaller and smaller, and it almost from 1.1 it goes down to about 0.4. So it almost decreases by about 50% or more than that, while we are increasing the TMAH concentration from 5% to 25%. So this temperature and the concentration both are like control parameter for TMAH etching. We can select suitable temperature and concentration, and accordingly can select the etch rate or can choose the etch rate. Ammonium phosphate, adding ammonium phosphate is gives us another control on TMAH etching. If we add 10% of ammonium phosphate in TMAH etching in the TMAH solution, then we can see that the etch rate actually increases, right. So without ammonium phosphate the etch rate is lesser, as you can see from this graph, for all the temperatures like 70, 80 and 90, for all the temperatures etch rate is lesser for the TMAH etching with without ammonium phosphate, whereas as we added ammonium phosphate, then we are getting higher etch rate. And also it gives smooth surface, which is also a requirement for many of the device application, because on top of that we deposit new material like metal electrode or some other kind of contact, and it will be, the contact will be better if we have a smooth surface. So adding ammonium phosphate also gives us advantage from that perspective. So now these are the important points related to TMAH etching. First of all is anisotropy, and here you can see that the 111 plane to 100 plane can have a selectivity of 1:10 to 1:35. That means that by the time 1 nanometer of 111 plane will be etched, 100 plane will etched by 10 nanometer to 35 nanometer, and that depends, like whether it will be 10 nanometer or 35 nanometer, that depends on the TMAH concentration, temperature, etc. parameters. But anisotropy will be always there. So the etching rate for 111 will be lesser, much lesser than the 100 plane. Next important point is selectivity, and as you can see here that the selectivity to against oxide is more than 1000. So this is very important, because by the time we etch 1 micron of silicon, only 1 nanometer of silicon dioxide will be etched with TMAH. So this can protect the silicon layer, whichever region we need to protect, we can use silicon dioxide layer to protect that, because this has a very good selectivity against oxide. Then similar to KOH, also if we dope the silicon with boron, then also we have a very high selectivity, like 100:1. So by the time the silicon, usual silicon will be etched to 100 nanometer, a boron doped silicon will be etched to only 1 nanometer. So this is another way of getting different kind of patterns by doping different regions according to our required design. Final thing is aluminum passivation. So in some cases we need where that after etching, that etched region will be passivated or protected. So if we add some amount of silicic acid to the TMAH, then we can get aluminum passivation in the region where it is etched. Now if we compare KOH, EDP and TMAH, then we can see that KOH is simple agent, and you can use it when no electronics is involved, because there are possibility of K plus ion actually penetrating into the silicon and changing the conductivity of the silicon semiconductor. So let us say if we are making some kind of electronic devices, and there we need for a particular transistor we need a specific mobility of the transistor or the semiconductor. So in that case, if we use KOH etching, then there is a possibility that KOH like the K plus ion might change the conductivity of the semiconductor layer or the silicon layer. So in those cases we should not use KOH, and we need a thicker mask layer, because as we were saying that KOH etches SiO2 also very aggressively, not as aggressive as silicon, but compared to TMAH it has much higher etching rate. So we need a thicker masking layer, and for KOH also we get very good anisotropy. The next agent EDP, which we have not discussed in this course, we should use where we have P plus H top, because EDP has a very good selectivity with respect to P plus H top, but the negative point is this is highly toxic, whereas TMAH is not toxic and this is highly compatible with CMOS, and it has all the good points of KOH also, and we can use it while making the CMOS technologies also. Now another aspect of KOH etching is convex corners. So that we will explain now with the help of this design. So let us say this is the design we need to etch, and this top white portion, whatever you can see here, this is the design, right, and this is the masking layer, and ultimately we are etching this pink layer which let us say is silicon. Now as you can see that these regions are protected, so these regions will not get etched, which is just below this white layer, this will not get etched, and this all the open areas will get etched very easily. So ultimately we should see the same kind of pattern in the silicon or on this pink layer. This white region can be some kind of polymer which is used as a masking layer or SiO2. So rounding up of these convex corners should not be there according to the design, but what happens is, see, this is like this corner is actually attacked from both the direction, like this direction as well as this direction, as we have seen for K-wedge etching, that we get a profile like this, right, where this angle is 54 degree, 54.7 degree, and then this plane is 111 plane. Plane is 111 plane. Now both of these, like this face also and this face also, both of these faces will have 111 plane, but this 111 plane will get easily attacked from this direction, as well as this 111 plane or the slope will get easily attacked from this direction. So because of that, this corner will get etched even more easily. So this convex corner will get etched even more easily, and so we will get something like this, where the actual surface was something like this, right, it get etched. In case of concave corner, the 111 planes actually, the protective planes actually join or merge here. So there is no point where the material can actually attack from this direction, because in this direction actually this 111 plane is there. So the concave corner are not etched aggressively where in compared to the convex corners. Now there are different ways to prevent this convex corner etching. The first method is that we can add 30% tertiary butyl. The first method is we can add 30% tertiary butanol solution or IPA to the 30% K-wedge solution. Okay. So this will reduce the etching rate at the convex corner. And another way is that we modify the mask according to our design. So that we will discuss in the next slide, like this. So technically we need a mask like this. Now as you have seen, the convex corner cut, because of the convex corner etching, it will become like this, right. Now what we can do is we can modify our design to add these extra portions here. Now adding this extra portion, what we have done, that now there does not exist any convex corner. There does not exist any convex corner. Only here is some concave corner which will not be affected because of that, and this extra region is also such that it will go under etching and it can get removed by the time the complete etching is done. So this dimension also we need to keep in mind, so that by the time our desired depth is etched, this region also should get etched. So ultimately the design after etching should come like this, without any convex corner cutting, and these regions will also not be there because of the under etching. And for that purpose, the width of the corner beam must be about twice the thickness of the square pattern. And there are actually commercially available programs are there which can, if we input our design, then accordingly it creates or modifies the mask so that the convex corner etching will not be there. Why it should be actually twice? Because let us say the thickness of this layer which you actually want to etch is about 1 micron, right. So, by the time we etch, it will go in the vertical direction by 1 micron. Now, in this 1 micron, it will try to etch laterally also, right, from this direction as well as from this direction it will etch 1 micron. So, if it is both the side, if it is coming 1 micron, then if the width is about 2 micron, then only by the time it etches 1 micron vertically, it will etch 2 micron horizontally. So, this complete region will get etched off, and the convex corner also will not be there, it will be a sharp corner. Finally, I am going to show these two patterns which are made by using anisotropic wet etching, and there you see this cantilever, and this is the SEM image or scanning electron microscope image of a real silicon dioxide cantilever which was made by KOH etching, because silicon got etched but SiO2 did not get etched. So, accordingly SiO2 remains as a freestanding beam, and this is the hollow region. You can see the shadow of the cantilever at the bottom part of the trench, and this cantilever is about length is about 65 micron, width is 15 micron, and thickness is about 500 nanometer. So, this was done by KOH etching. And the next example is of an AFM tip, and AFM tip is etched by just like that. This is, let us say, the mask, and below there is silicon. Now, all the sides silicon will get etched and 111 planes will get opened up. Now, as this one, because of the convex etching, as this 111 planes are getting etched from the convex corner also, the 411 plane comes into the picture, like 411 planes get opened up, and because of that, see that this region, if this is the mask, then the middle portion will get etched at last, because it will take time for the etchant to come in contact with this, right, and the side regions will get etched fast. So, it will ultimately become like a pyramid shape, because the top region will get first etched. So, the etching rate or the most region will get etched from the top initially, and then as it opens up, slowly it goes down, and then it etches from the bottom also, and by the time it reaches our desired depth, the top portion has almost reached the central point. So, you get a sharp tip which is used for atomic force microscopy. So, these two both of these structures were made in SENS IIT Bangalore by Professor Ken Mutt, and with this we will stop for this class, and next time we will discuss on lithography. Thank you.